electrolytic reduction. Electrolytic reduction. Just write one point for highly reactive metal oxides. Highly reactive metal oxides. Highly reactive metal oxides reduced by electrolytic reduction only. Electrolytic reduction only. Example, if you take first group, second group elements are highly reactive, not only first and second group elements, even aluminium also, it is highly reactive. So even
Sir, can you repeat again?
Which point, Amma?
The just now you said the point, no, sir.
Highly reactive metal oxides. Highly reactive metal oxides reduced by electrolytic reduction, because no other reducing agent can reduce highly reactive metal oxides like first group elements, second group elements, and aluminium oxide also. In that aluminium oxide also, that electrolytic reduction we will use. Okay. Next stage is refining process. Important, students. Fourth stage is refining process. Refining process. Which metals oxides undergo self-reduction, students? Which metal undergo self-reduction?
Mercury, copper, and lead.
Copper, mercury, lead, or undergo self-reduction. Undergo self-reduction. Very good. Next one. So in third stage, we are getting crude metals. Crude metals only we are using. Still, they contain some impurities. They are not even 99% pure. In this refining process, we are removing that impurities which they have, which we can't remove in above stages, that we are removing in refining process. Refining process. Here also we can't tell 100% pure, it is 99%. If still advanced method means 99.9% pure. Don't write anywhere 100% pure. Okay, then we are not sincere. Okay, students. Now refining process. There are different methods. One is liquefaction in this refining process also. What is liquefaction, students? Liquefaction.
You will liquefy the ore, heat it very, like melt it.
Liquefaction means it's like melting only, converting into liquid form. Converting into liquid form. So this, in this process, what we are doing, students? So this mixture we are powdered ore we are heating. This metal is there, no crude metal. What we are getting, that powdered form. Otherwise, use metal with impurities. Metal with the impurities we are heating. After heating, is applicable for low melting point metals. It is applicable for low melting point metals. So once if we heat, these low melting point metals, they melt and they move in, the flow by leaving impurities. By leaving impurities, impurities will be crystallized over there, and pure metal will flow into another end. So here what you have to write, it is applicable for low melting point metals. Applicable for low melting point metals like zinc, lead, and low melting point metals. Through filtration, we can separate it. Pure metal will convert into molten form, impurities will be left behind. So through filtration, we can separate liquefaction. It is easy process only. Next one, distillation. Same you had in 9th standard, I think, distillation. This one also applicable for low boiling point metals. Low boiling point metals. In liquefaction, what we are doing by heating, we are converting metal into liquid form. In distillation, what we are doing, we are converting metal into vapor form.
Yeah.
Vapor form. So through condensation, we will get it in liquid state. Once if it get cool, if we cool no, then it will crystallize out. Crystallize out. Same process what you are doing in 9th standard for purification of elements. Same thing. This method is otherwise you write nano principle. This method is based on the differences between boiling points of metal and impurities. Differences in the boiling points of metal and impurities. So low boiling point metals get vaporized. Then through condenser, we will cool it afterwards, crystallize out. Impurities will be left over there. So you can use zinc. This we can use for zinc, mercury. Same method. These are not that important, but zone refining is there. Very, very important, students. This one, zone refining. Zone refining process. Listen carefully. About two are not that important, but this one onwards it's important. Zone refining process. So in zone refining process, first we are converting this impure metal into rod form. Metal rod. Then here heating coils we are using. These are circular heating coils. They can move from one end to another end. Listen carefully. Once this heating coils, once it is rod get heats, no. Here metal is having high melting point. Impurities are having low melting point. Here we will select. Stravan is asking which are the low boiling point metals. Stravan, 12th group elements zinc, mercury, cadmium are having low melting and boiling points since they have completely filled d orbitals. If they have completely filled d orbitals, metals are strong because of metallic bonds. These metallic bonds in the transition elements, especially through dd transitions, they become strong. Unpaired electron of 1d orbital combines with unpaired orbital of unpaired electron of another orbital. So number of unpaired electrons increase, number of dd transitions also increase, or dd interactions. Transition we can't say, dd interactions we can say. One metal atom d orbital will interact with another metal orbital. So in case of 12th group elements, since all the d orbitals completely filled, if you take zinc configuration, zinc atomic number 30, its electronic configuration is argon 4s2 3d10. Here S is completely filled, D is completely filled. If orbital is completely filled, they won't undergo interactions effectively like unpaired electron. Students, do you know the difference between unpaired electron and paired electrons in orbitals?
Yes.
Unpaired means single electron, paired means two electrons will be there with opposite
Orbital.
spins. Yes. So here, if it is unpaired orbital, it will have interaction with another orbital. The orbital. So 12th group elements are having low melting points. So here, circular heating coils, when circular heating coils moving from one end to another end, I told even metal above its, just above the melting point of the metal, we will heat. So first, impurities will melt because their melting points are lower than metal melting points. They both will melt, but these impurities will go to one slowly. It will be like little slope will be there. This will go to another end after converting into. But once heating coil moving from here to there, if we are heating coil moving from here to here, automatically metal here become little cool, no? It will solidify here. But impurities will not. Impurities will not become solidified. They won't convert into solid form. Only metal temperature, if we make it little less, moving heating coil from here to another end, it will be solidified or crystallized. But impurities will not get crystallized. They move to another end. Like this repeatedly, if we do, impurities will flow to this end. Here, impurities concentration increases gradually. Then after reaching certain condition, we'll cut this part so that we'll get only. So here all this pure metal rod it is. Here impurities. Here concentration of the impurities another end increases. So finally we'll cut this part so that we'll get pure form. This is zone refining. Once again I repeat, students, this is the metal rod. Here heating coils will keep. These heating coils move from one end to another end. When moving heating coil heats the temperature increase, once heating coil comes, then metal and impurities, because we are heating above the melting point of the metal, little just above the melting point of metal. Once heating coil moves from this end to this end, metal crystallizes here only. Metal crystallizes here only, but impurities that molten form, because their melting points are very low, so they won't convert into solid form easily. They move to another end. They concentrate here. They concentrate here. Repeatedly, if we do, all the impurities will move to another end. Only pure metal crystallize here. Only pure metal crystallize here. So once if we confirm all the impurities left from this, we can cut the part and we can separate it so that we'll get pure form. In this, whatever the metal, we are getting 99% pure. 99% pure. Here, impurities are having less low melting points. Low melting points than metal. Point. So impurities melt and move to another end. Metal crystallize at that position only. On heating, impurities melt other end. metal crystallize over there. In one competitive examination, they asked, among the following, in which process crystallization takes place? Crystallization takes place in zone refining. In zone refining, metal melting point is little higher than impurities. So once if we hit just above the melting point of the metal, it will melt, but soon after melting again it converted to solid form. But impurities will not melt, will not convert into solid form. They move to other end. This is only the basic principle. Maximum they won't ask any definition and all. This is not definition, just points if you write enough. And important one is for competitive examination, NTSC or any other examinations. Which metal is which among the following which is refined by zone refining process? Which is refined by zone refining process? They are asking. So this method is used to refine. This method is used to refine the elements which are used in semiconductor devices like silicon, germanium, helium, etc. Because they must be.
Sir, gallium has a very low melting point, no, sir.
Sorry?
Helium has very low melting point, right?
Yeah, it will melt easily. Gallium is used. Gallium cut it because already it is in at room temperature and it will melt. Don't want, because it will move with the impurities. Silicon, germanium you use. Even 15th group elements are there, no? Some elements are used in semiconductor devices. Silicon, germanium, or simply you can write based on the options you can select which are used in semiconductor devices. Semiconductors. This is about zone refining. Next, one more is there, electrolytic refining. Electrolytic refining. In this one, so which metal we are going to refine, that metal will take as anode, positively charged electrode, and same pure metal will take, suppose if you are refining copper, impure copper is acting as anode, and pure metal acts as cathode. Act as cathode. And here electrolyte purpose we are using the respective metal sulfate solution. Metal sulfate. If it is copper, copper sulfate we use. So you know on electrolysis, metal is at anode. Every time, remember students, at anode oxidation takes place. What is oxidation, students? What is oxidation?
Loss of electrons.
Oxidation is nothing but loss of electrons. Very good. So here metal is losing electrons. It is converting into, suppose a divalent I will take. So it loses 2 electrons. So it is converting into ionic form. Slowly it will move towards the pure metal and deposit here. It will move to the cathode. So at cathode, reduction takes place. Cathode reduction takes place. See here, M2 plus is gaining 2 electrons. It's converting into M. So this so here deposit. After some time, we'll remove the cathode and we'll scratch it, so that we'll get pure metal. This is electrolytic refining. So anyway, copper metallurgy is there. There you will learn. In electrolytic refining process, what we are doing, students? Impure metal acts as anode, impure metal acts as anode, pure metal acts as cathode, pure metal acts as cathode. On passing electrolysis, metal oxidized to impure metal oxidized to anionic form. Slowly it moves towards a pure metal, means cathode, where it undergo reduction. Only so much. Here, if you want, you can use copper also. Copper, if you use, we can give some extra points. See, students, I will replace M with copper. I want to give two important points here. Copper sulfate solution. Nothing is there to change. Only reactions if you change enough. At anode, Cu is oxidized to Cu2 plus 2 electrons. At cathode, Cu is gaining 2 electrons and becoming your Cu. Next, so it is moving towards cathode, and it is next impurities like heavy metal, impurities like silver, gold settles under anode, or like highly reactive metals, first group elements, second group elements. If those metals are there, they dissolve in the electrolytic solution, but these metals will not dissolve in the electrolytic solution. They just settle at anode. This is called impurities which are settling at anode. Those are called anode mud. That composition, what we call anode mud. Anode mud. Anode mud contains mainly silver, gold. So you may get doubts, sir. How can you say gold and silver impurities? They are precious than copper,
We
right?
are looking for copper, that is right.
Not only that, so extraction of silver and gold, it's very risky process here. That extraction may cross that. It is highly expensive one way. It's highly expensive. After doing so much work, also whatever the amount we are getting, it will be less. So all the cases, if we consider, extraction is waste.
Loss.
So we won't extract. Anode mud contains silver, gold. This one also in NEET examinations and all they are asking. So here in refining process, which and all methods we discussed, one is liquation. Liquation is like melting only. Lower melting point impurities or metals will move. If metal is having lower melting point, it will melt. Impurities will be left behind it. Through filtration, we can separate. In that distillation we are converting lower melting point components into vaporized form. After condensation, it will become solid form. So impurities will be left in that container only. Distillation chamber only. Next, zone refining. I told you, in zone refining process, which metal you are going to refine, that metal you have to convert into rod form. Then with movable circular heating coils, we are heating the rod, that movable reheating coils. So here impurities are having lower melting points than metals. Still we are heating in the rod just above the melting points of metal, so that both convert into molten form. But once moving coil moves away from the metal, means move to other end, metal crystallize but not impurities. So impurities will move into another end. So other end will get concentrated with impurities. After doing repeatedly, we will do this process. Afterwards, we'll cut the impurities part so that we'll get pure metal. This is about electrolytic, zone refining process. Next, electrolytic refining process, what we are doing. In electrolytic refining process, impure metal acts as anode, pure metal acts as cathode. Respective metal sulfate solution we are taking as electrolyte. On passing electrolysis, impure metal get oxidized to respective ionic form. Then slowly it moves to cathode and there it deposit. There it undergo reduction and deposit. So in this way, in electrolytic reduction, we are refining. It is especially for copper ores, copper metal and all. Next one, vapor phase refining. Properly, if you learn all these things, in second year, nothing is there to learn in metallurgy, refining process. Vapor phase refining. Stop writing, students, all of you. In vapor phase refining, what we are doing? So here one metal, suppose nickel is there. Nickel we are heating with suitable reagent, so that it will form only nickel can form complex with the reagent. In that way we will select and impurities will not react, so that it forms. And while forming the complex also it should form unstable complex. If it forms stable complex we can't extract. Again that is one more work for us to get metal from the compound. So what we are doing, I will give here in vapor phase refining process. Mond's process is there, very very important, very easy and important. Last year also they asked JEE means they asked this question. Mond's process is used to refine. Mond's process is used to refine nickel. So here it is impure nickel, students. Simply we can tell nickel with impurities. On heating with carbon monoxide, it forms nickel tetracarbonyl complex. Nickel tetracarbonyl complex. This is unstable. This one is unstable. This unstable complex on heating above 1200 degrees. If you don't know temperature, leave it. You can write just delta symbol. Now you may get doubt. Sir, what Ganakarya you did? Nickel plus 4 CO you wrote, afterwards again nickel plus 4 CO you wrote. Nothing happened, no, this process.
But impurities got separated.
Impurities got separated. Here only nickel reacted, but not impurities. So impurities left here only. Understood, students? By using one suitable reagent group, we are forming. And I told you, condition, it must be unstable complex. If it is stable one, again extraction from this component is very difficult, and we need to follow one more method. It should form temporary complex. Soon after heating, it will carbon monoxide will leave, pure nickel will get. Impure nickel you can write, or nickel with impurities, or with impurities you put. Understood, students?
Yes, sir.
The triangle means heating, no, sir?
Sorry?
The triangle means heating on the arrow.
Yes, yes, yes. Heating symbol it is.
Sir, usually what are the impurities?
In this,
Generally, metal.
it contains some non-metals and all. Mainly non-metals will not react with the carbon monoxide, right? And impurity generally it contains manganese, won't be there. Nickel generally contains non-metallic impurities like arsenic and all. They won't react with the carbon monoxides. Next one more is Van Arkel process. Van Arkel process. Same method, but reagent will change. Here, titanium, zirconium, even mercury also we can use, or mercury also we can use the same method. See here, any one I'll take titanium. Here, iodine we are using, iodine. On heating, it forms tetraiodo complex. This one also unstable only. Students, this is with impurities. Next, once if we heat this one, it forms titanium plus iodine. Pure one. (1200 degrees Celsius around. Okay, students, we'll so zone refining, vapor phase refining also over. Here now, what I am going to give till extra students is in PU2. Should I give? But you can understand, not a problem. Should I give students?
Yes, sir.
Actually, 4-5 metals from extraction is there. Everything, all the process will include in that. No, Shravan, simply I said. We should learn. Aluminium metallurgy you put right. One metal if I do, you'll come to know what is the process. Aluminium metallurgy. Aluminium metallurgy. Aluminium metallurgy. What are the ores of aluminium, students? Anyone can you tell?
Al2O3.
Al2O3, XH2O. What is the name of this one?
Bauxite.
Bauxite. Next, Na3Al(F6) is also ore of aluminium only. Cryolite. Sorry, sir. Cryolite. Okay. Now, first step is concentration of aluminum. Alumina is nothing but Al2O3, students. Aluminium means Al. Alumina means Al2O3. Like silica, silicon. Silicon means only silicon atom or silicon, Si, but silica means SiO2. So like this, like that, even alumina means Al2O3. Better ore is alumina. Alumina is the better ore. So, yeah, economically, even extraction also easy. Bauxite ore. So concentration of alumina. In this concentration of alumina, first, what are the impurities present in this Al2 bauxite ore? There are impurities like iron oxide and silica are the main impurities present in the ore. These are the expected impurities. Next. Sometimes it may contain both impurities, sometimes it contain only one impurity. If it contains both impurities, then it is called red bauxite. See students, red bauxite contains iron oxide is major impurity. This is the major impurity. Each and every point, please note down students, very, very important. Impurity. SiO2 is little minor impurity. Little bit SiO2 is present in red bauxite. Next, white bauxite. It contains only silica as impurity. It contains silica impurity. Yeah, alumina with 2 moles of water is bauxite. Shravan is there here?
Yes, sir.
Bauxite is the main ore for aluminium. So main ore means extraction is difficult, easy, and economically it is little profitable. Then
So
only
what is alumina?
Al2O3. Anhydride form of bauxite. Al2O3 is alumina. Shravan, can you hear me?
Yes, sir.
Okay, in that possible impurities are iron oxide and silica. Iron oxide and silica. If both impurities are there, then that is called red bauxite. In that main impurity is iron oxide. SiO2 is in minor quantities. Next one, white bauxite contains only silica as impurity. Sometimes the direct questions they are asking. What is white bauxite? What is the red bauxite? What are the impurities present in red bauxite? What are the impurities present in white bauxite? Like that, they are asking. White bauxite contains only silica as impurity. Red bauxite contains silica at the same time iron oxide, but iron oxide is the major impurity. So how to separate these? If both are there, how to separate? If only one is there, how to separate? There are methods in this. First one is Bayer's process. Put star marks and write students. Bayer's process. Bayer's process. Bayer's process is used to concentrate red bauxite. Hope you understood which impurities we are going to remove. It is used to concentrate red bauxite. Which impurities we are removing, students?
Iron oxide and
Only iron oxide. Chinmay?
and Si2.
SiO2. Both can be separated in this method. So what is the Bayer's process? See students, listen carefully, because it won't be there in NCERT, also in 12th standard, but it is important for competitive examination. Al2O3 on reaction with sodium hydroxide. You may get doubts, or aluminum oxide is aluminum is metal, metal oxides are basic. Again, it is reacting with base. It can react since it is
Amphoteric. I mean,
amphoteric.
aluminium. Right?
Among the following, in which method is used amphoteric nature advantage of aluminium purification? In this method only, where we are using base, There amphoteric character only we are using advantage. So it forms NaAlO2, NaAlO2 plus H2O. This is called sodium aluminate or sodium metaaluminate. Sodium aluminate or sodium metaaluminate. Listen students, how we are going to separate here SiO2 and FeO impurities. This one is soluble in water, but these impurities will not soluble. You know, iron oxide will not soluble, silica will not soluble in water. So these impurities will be left a solution. This will form soluble. It is soluble in water. NaAlO2 on hydrolysis. We want to remove now sodium from this. We don't want sodium, right? So on hydrolysis, aluminium hydroxide will form and sodium hydroxide. Which one we used earlier, that is separated here. Now impurities left in first stage only. Through filtration we will separate. NaAlO2 will soluble. FeO and SiO2 are not soluble through filtration. Soluble and insoluble can be separated by using filtration. So we can separate by using filtration. These impurities will be removed in the first stage through filtration. Afterwards, on hydrolysis, we are getting aluminum hydroxide, sodium hydroxide gets separated. This aluminum hydroxide, it is a precipitate. On heating above 1200 degrees Celsius, I told you, students, if you don't know the temperature, no need to write, just a delta symbol you put, forms Al2O3 plus H2O. This is concentrated, which is free from the above impurities. Understood, students? Just by using base, we are removing aluminum from the impurities. So we are selecting base in such a way that it should soluble in water. So we are making it soluble in water. So impurities are not soluble in water. Through filtration, we are separating impurities and concentrated ore. Okay, students. Bayer's process, you understood now? So how they are asking questions upon this? In Bayer's process, among the following, which is used in Bayer's process? In which process amphoteric nature has taken advantage for the purification? In Bayer's process. Even Hall's process is there. There also we will take base only. Amphoteric nature only we will use. Okay. Here, base is forming one compound which is water soluble. Their impurities are not soluble, so that we can separate impurities from the pure concentrated ore through by using filtration. Afterwards, we want to remove even sodium hydroxide also, sodium present in sodium aluminate also we want to remove. Simply hydrolysis will get, it will get separated out. Then aluminum hydroxide, it is a precipitate, this is a soluble compound. So aluminum hydroxide on heating again converted to Al2O3, which is concentrated. Next one, Hall's process. Hall's process. Here also same thing, Al2O3. Base, there which base we use? Sodium hydroxide we used. Here sodium carbonate we are using. This one also basic, mild basic. Sodium carbonate. Product is same, students. NaAlO2. Carbonates, if they react with other compounds, they release carbon dioxide.
Yeah.
Carbon dioxide.
Carbon dioxide. Yes. Here XH2O you take. There also you take if you want. H2O will form. XH2, since bauxite contain water molecules, 2 water molecules. Next, here NaAlO2 plus CO2 plus H2, whatever release there is right here. It forms aluminium hydroxide plus NaHCO3. Sodium bicarbonate. Sodium here, the sodium
Baking
is
soda.
removing. Emma? No, no,
Baking
sodium
soda.
carbonate only you keep. How it is joining, in that way only it will come out. Na2CO3. Sodium carbonate. Next, third step is same. Plus H2. Same thing. This one also used to remove both impurities. Simply you can write red box. So
Then we have to reduce, right? Al2O3.
yeah. Next, that is in a smelting process. Next one,
Or electrolytic reduction.
electrolytic reduction. Electrolytic reduction we will use for aluminium oxide. Next one, Serpeck process. Serpeck process. Serpeck process. When we use this one, students, if silica as impurity,
For
mainly,
white bauxite.
yes, silica as impurity, or simply you can write here which ore we are concentrating, white bauxite. See students, Al2O3, Al2O3 upon this coke, carbon in the form of coke, and nitrogen we are adding. Nitrogen. It forms aluminium nitride. Aluminium nitride. Carbon will remove oxygen so that carbon monoxide will form. Carbon monoxide will form. Next one, aluminium nitride on hydrolysis. Aluminium nitride on hydrolysis gives aluminium hydroxide and ammonia. Ammonia gas. See students, metal nitrides on hydrolysis gives ammonia gas, and respective metal hydroxide you will get. Copy this.
Yes, sir.
Done, students?
Yes, sir.
Okay, once if you get aluminium hydroxide, process is same. Heat above 1200 degrees, Al2O3, H2O. You will get. H2O. And here silica, how it is removed. See students, silica impurity react with carbon monoxide, which is avoided second step. So it reacts with carbon monoxide and silica. So silica is converting into silicon. It is reduced to silicon. Easily at that temperature, easily it vaporizes silicon. Carbon dioxide, anyway, it is gas, it will be separated out. In this way, we are removing silica impurity. Okay, students. Base process sodium hydroxide we used. Hall's process sodium carbonate we used. In both process, both process used to remove silica and iron oxide impurities. And the last one, Serpeck's process, here only silica impurities can be separated. This is Serpeck's process. S for silica, you remember. In Serpeck's process, which impurity is removed? Silica. If bauxite contains silica, it is called white bauxite. Then students, next one. So anyway, concentrated alumina we got. Next one is reduction. Electrolytic reduction. Electrolytic reduction, because other years in carbon monoxide and all, they can't reduce this metal oxide, aluminium oxide. So electricity we are using. So these are the graphite rods, students. This is copper clamp. Anode. Graphite rods. Next one. This is the steel tank, which is lined with let it be inside, whatever the lining is there, no, that is carbon lining. Inside carbon lining. So which is acting as cathode. This one is there, your books, study material. Next one, here alumina, concentrated alumina is there, no? Al2O3 mixed with Na3AlF6, important students, and calcium chloride. This is nothing but fluorspar. So what is the purpose of using fluorspar here? I will tell. Understood, students? Diagram. Here, series of graphite rods we are using, acting as anode. With steel tank, carbon lining we are keeping, that acts as cathode. Cathode has which charge, students? Positive or negative charge?
Positive.
Cathode has
Negative charge.
Negative.
Tell me, positive or negative?
Negative charge. Negative.
Because remember, cathode has to attract cation. Cathode has to attract cation. To attract cation, it must have negative charge, isn't it? Anode charge is positive. So don't get confusion, students. Cation charge is positive, cathode charge is negative. Cathode, why we are calling it, is attracting cation. Okay, students. Now, this story we'll see. With aluminium oxide, we are adding Na3AlF6. What is the name of Na3AlF6, students?
No. Any
Triona.
cryo something.
Yeah, correct.
Cryotite.
Triolite.
Tri-
CaF2
Trilite.
light LIT cryolite. CaF2
Calcium fluoride.
fluorspar.
Okay.
Fluorspar we are adding. What is the purpose of adding these two? Listen, students. Aluminium oxide. Its melting point is very high, almost 1800 degrees Celsius. Its melting point is very high. At the same time, its conductivity is less. Both are disadvantages for electrolytic reduction, electrolysis process. We have to convert into molten form only, no? If they convert into molten form, then only they can conduct electricity. One more, if they are converting into molten form only, high temperature we have to use. At that time, at the temperature, even this container also can melt. Before melting aluminum oxide, this iron, this tank, whatever we are using, that will melt. So that is one big disadvantage. And conductivity is very less. So we are adding these two chemicals to increase electrical conductivity and decrease melting point. Purpose of adding cryolite and fluorspar is to decrease the melting point and increase electrical conductivity. Write that point, students. Cryolite and fluorspar is added to the mixture. To decrease the melting point and increase the electrical conductivity of aluminum oxide.
Sir, what is that third bar to the left?
Which one?
The other two bars are there, right? They're also graphite only.
Graphite only. Series, because carbon will consume very fast in this. I will tell why it will consume. Okay. Purpose of adding fluorspar and cryolite is to increase the electrical conductivity and to decrease the melting point. So melting point of decrease up to 900 degrees Celsius, so that melting process will be easy. So now here one more important thing is writing chemical reactions. First, Na3AlF6, it is initiating, no? It converted to NaF plus AlF3. At anode, I told you, at anode always oxidation takes place. Sorry, one more step is there. Afterwards, I'll write anode cathode reactions. AlF3 is converting into Al3 plus 3F minus. So those reaction generally takes place at cathode. At cathode, what happens, students? This metal ion undergo reduction by gaining 3 electrons. Aluminium. Next one, at anode oxidation takes place. You just write here reduction. Space. At anode oxidation takes place. How it takes place? See here. 3F minus is converting into 3F by releasing 3 electrons. This will react with the aluminium oxide. See, students. Fluorine I will write here. AlF3 plus O2. AlF3 plus O2. So 3O2, if I write 4Al, I have to take here. So here, how many fluorines we need to take? 12. 12 fluorines. Finally, Al2O3 is converting into AlF3. Our process is same. Next, this oxygen released is there, no? It will move towards O minus to S, right? Oxide form. It will move towards graphite anode and forms carbon monoxide by the release of 2 electrons. Otherwise, if 2 moles of oxide ions released from this release, then it form carbon dioxide and 4 electrons. So however they release the carbon monoxide or carbon dioxide, whatever the form it is reacting with carbon anode. So we periodically have to we have to change the graphite rods. Since oxygen released here reacting with carbon, so the size of graphite rods will get reduced because here it is consuming. That is the reason 3 we are keeping, and we have to we have to change the graphite rod frequently. This way we will reduce the aluminium. So from concentration of the ore, all types, to extraction of metal, pure metal, everything we discussed this. And name of this process I didn't tell. Hall Herold process. Herold process. Hall Herold process. In competitive examination, they are asking applications. Okay, students. So today, which and all topics we covered? Refining process, all types we finished. Next one, aluminium metallurgy. Next, in vapor phase refining, vanillin process, Mond's process. Mond's process is for refining of. Mond's process is used for refining of. Emma, how many chapters left? Only carbon and its compounds left, right?
Yeah, that is organic chemistry, right?
Yeah, that's what, organic chemistry. Other than that, anything is pending?
No, sir. I think we finished for volume 1. Yeah, and it's used for refining nickel.
It is used for refining nickel. Kripali, I told last time, I think, state board book you read, any extra questions, if they ask, our foundation is more than enough. If you use this synopsis, difficult level, by keeping their head down, legs up, they prepare question paper also, you can answer. Maximum in this only will be there. So other theoretical process purpose, not nuclear chemistry. This one, metallurgy also important. Metals and non-metals concept is also important. In that, metallurgy important. One time they asked which flux is used in. Sorry, what is the purpose of adding silica in calcium carbonate in iron metallurgy? They asked purpose of addition of calcium carbonate in iron metallurgy. Do you know, students, what is the purpose?
It is a flux.
Yes. Calcium carbonate on heating, it gives calcium oxide, which is used as flux. So like that, they are asking from the inner the process, inside the process, they are asking questions. That anyway, while explaining the topic, I will cover how they are asking questions also. So that like that, you other chapters also prepare. Even organic chemistry also. One time they asked homologous series differed by molecular mass they gave. Here, what is homologous series, students? Do you know homologous series? Don't know, I think, because carbon and its compounds not over now. And homologous series.
New topic.
Sorry, new topic. Ethane, propane, butane, like that. each unit is differ by CH2, right? Each compound is differ by 1 CH2 unit. Okay, that property is same, number of carbon atoms increases. They differ by CH2 units. That is CH2 unit molecular mass, if you put enough, 14 units. That is only answer. That I will tell. While teaching organic chemistry, I will tell how they are asking questions.